Okay, everybody. Can everyone hear me? Would you say yes? Looks like you can't really hear me. Okay, good. Thank you very much. So let's get started. So last time we talked about resolutions, which is a particular kind of proof system for proof calculus for propositional logic. The idea of resolution is a bit like derivation, proof by contradiction, okay? So we have a conjunctive CNF formula, and then we apply what proof rule in the resolution, which is a way to derive a reservant from two clauses. And then the process of deriving reservant is a bit like canceling some literals in two clauses. And then we show that using resolution, we can prove, we can derive, we can show that certain given set CNF formula is unsatisfiable. And in fact, the resolution proof system or resolution calculus is powerful enough to prove all the unsatisfiable statements. So that is, what I just said correspond to what I called soundness and completeness of resolution proof system. But now we can ask the more algorithmic question. We talk about resolution calculus, which is a bit like some rules or some methodology that we can use to prove a certain given propositional logic formula is satisfiable or not. But we didn't really tell, that calculus doesn't really tell us how we can come up with an algorithm that can prove unsatisfiability of a given formula. And there are multiple ways of using resolution calculus to derive an algorithm. And what we're going to talk about now is one particular well-known algorithm called Davy-Putnam procedure. Okay, and although what we're going to talk about next, which is called DPLL, will form the basis of modern set solver. This Davy-Putnam procedure is a basis of, in some sense, it's a basis of DPLL. And you will see, the key ideas of this procedure is used in a set solver, as well as sometimes something very similar appears in probabilistic inference algorithms called variable elimination. Okay, so so these are the guys, I think this is David and this is perhaps Putnam, and they are the ones who invented this procedure. Yeah, so let me just give us some overview about this algorithm. So this algorithm is, the goal of this algorithm is to prove a given CNF formula is unsatisfiable. Okay, so now the algorithm is given. Okay, maybe. Yeah, the algorithm is given CNF formula F, which has multiple literals, it's like the multiple clauses, C1 and C2 and so on. We'll have a bunch of clauses, and each clause is a disjunction of literals, CLN. Okay, and then the formula F, because it's a finite formula, there will be finitely many propositional variables appearing in F. So propositional variable P1 up to, let's erase this guy because it's a bit confusing. So maybe there are propositional variable P1 up to Pn. Okay, so that's the situation that we are given. Our job is to say whether F is satisfiable or not. And in fact, what we are really asking for is if F is satisfiable, we want to have a satisfying assignment for these propositional variable P1 up to Pn. That's because F often encodes some of the problems that we care about. Satisfying assignment is a solution for the problem that we care about. Okay, so now how does the algorithm works in very high level? The algorithm works by transforming F to, it's an iterative algorithm. It's transforming F to F1 by doing some manipulation on these clauses. But the key property of F1 is that F1 uses a less variable. So it uses propositional variable P1 up to Pn minus 1. So that's a property number 1. Property number 2 is F1 is closely related to the formula that we are given. Let's call it F0. So F0 and F1 are EQ satisfiable. So this doesn't mean F1 and F0 and F1 are equivalent, okay? It just means that F0 is satisfiable precisely when, in other words, if and only if F1 is satisfiable. We don't know F1 is satisfiable or not, but we do know that they are equally, they are equisatisfiable, okay? So as far as satisfiability is concerned, they are the same thing. They say the same thing. And then the next step is it generate F2. In the case of F2, it uses one less fewer variables for F1 up to P1 up to Pn minus 2. And then it also has the property F1 and F2 are equisatisfiable. And then it keep continue, okay, until it reaches, say, maybe Fn or Fn minus 1. I don't quite make the index right. But if you reach the final case, then there are no propositional variable at all, okay? Because all the variables are eliminated one by one. At the end, we have a no propositional variable, which means that, I mean, if you do some simplification, this Fn will be either empty, so it's gonna be equal to true. I mean, in the representation, that representation we talk about, that's going to be represented by an empty set. Or another possibility is it's equal to false. And that is going to be represented as a singleton set which contains empty, and which we often wrote it as set containing box. Okay, so it's going to be either one of these cases. I mean, we know that's because it doesn't have any propositional variable at all, and it's a CNF formula. So then we can easily decide whether this Fn is satisfiable or not. The first case, this case is satisfiable. It's always true. And this case is unsatisfiable. So in the base case, it's really easy. Now, once you get the answer at the Fn, then we can, because of the property I talk about, in this equisatisfiability property I talk about, if we know that Fn is satisfiable, then Fn minus 1 is satisfiable, Fn minus 2 is satisfiable, and so on. So then we can say F0 is satisfiable. If Fn is unsatisfiable, then we know Fn minus 1 is unsatisfiable, and so on, so that we can also say F0 is unsatisfiable. So that's how this, I mean, the kind of big picture of this algorithm. The algorithm starts with F0 and produce equisatisfiable formula, but one fewer variables. And as it continues to do this process until we reach the base case, for which we can easily make the decisions about satisfiability or unsatisfiability. Okay. So that's the idea. But then the relationship between this David-Putnam procedure and resolution calculus is, when we go from F0 to F1, sometimes we use resolution to generate F1 from F0. Okay, so resolution is a key step to remove the variable. So if you see F0 and F1, the key, really what's achieved by going from F0 to F1 is removing this propositional variable Pn. Sometimes it can be easily eliminated, but in most general case, we have to use resolution to get rid of it. Okay, that's the overall picture of the algorithm. Then let's study a bit more. Okay, so here's how the algorithm works. So the key step of the algorithm is what's called variable elimination. That corresponds to moving F1 to Fn minus 1, or Fn minus 1 to Fn minus 2, and so on. Okay, each step of moving from larger formula into the next formula, which uses one fewer variable, that's what this variable elimination is doing. Okay, so its job, as that its title said, is removing the variable is what it's supposed to do. And then And then it does the case on, deciding which variable to eliminate, that's some kind of meta decisions to be made, okay? In the example that I showed you, I said, it's just we kind of list all the variable, we remove variable from the last, but algorithm make a different decision, okay? But once the algorithm decide to remove variable p, then you do case split. The first case is if the variable p appears in the formula f only positively, which means that formula f, so let's use blue, yeah, which means that if we have a formula f and variable p appears, but it always appears as a positive literals. Maybe sometimes it doesn't appear, okay, and so on. But it always appears as a positive literal. In that case, the way we eliminate this variable is we do it by replacing p by true, okay? Then why is that? That's because now if you think about, there are two possible ways of instantiating p. One is setting p to true. The other is setting p to false. Okay, so these are the two possibilities. Now, if you think about the formula f, if we set p to false, okay, then this formula f is is less likely to be satisfiable. And if we set p to true, it's more likely to be satisfied. That's because if we set p to true, at least these two guys will become automatically satisfiable, so we don't have to worry about them. But if we set p to false, okay, so if you set p to false, then these two guys will not, these two guys, we don't really know it's satisfiable or not. This part, this disjunction part will disappear because p is now false. So then we have a bit harder problem, which is we have to satisfy everything that appears on the rest, as well as these two extra guys. That's what, this case. The above case is easier, much easier to satisfy. In other words, if f has a satisfying assignment with p to be false, it also has a satisfying assignment with p to be with p set to true, because p only appears positively. Okay, so it's a bit like we want to set p to something, but then in this case, setting p to true doesn't lose anything. So that's why we can do it this way. Okay. No, erasure. Right. So, and the next case is if formula f, inside the formula, if p appears only negatively, like this, so on. So in that case, the situation is exactly the opposite. If you set p to false, then these two formulas, this clause and then this clause, they're gonna be true because p is false, negation of p is true, and these two guys will be satisfied, so we don't have to worry about it, and then we can just focus on the rest. Okay, and just like I said, we don't lose anything by setting p to false. In other words, this formula f is satisfiable, then setting p to true will not change this satisfiability. Okay, and p to false will not change the satisfiability. I'm saying I think it's something obvious in both cases. If p appears only positively, setting p to true doesn't lose anything. If p appears only negatively, setting p to false doesn't lose anything. So that's how we can get rid of this propositional variable p. Now the most tricky part is if p appears positively as well as negatively. So then in that case, so let's write it here. So if the p appears positively and negatively, so then we have some of the clause where p appears positively. And then some other clauses where p appears negatively. and then some other clause where P doesn't appear anywhere. Okay, so there are three kinds of clauses. So then in that case, we apply resolution. So then, and we can apply resolutions for with respect to P. Okay, for these two guys, I mean this guy and this guy, we can apply the resolution because P appears positively one case, P appears negatively other case. Then we consider all the possible combinations between the clause that contain P as a positive occurrence, clause that contains P as a negative occurrence. We consider all of their possible combinations. So there are this combination, and then this combinations. Another combination is this combination and this combination. So there are four possible ways of bringing things together. For all those combinations, we apply the resolution. Okay, so then applying that, in this case we have to apply resolution 4 times, the resolution proof for 4 times, and then that will give us 4 reservoirs. Okay, and then we conjoin to this 4 reservoirs to say C1, C2 to C4, and we conjoin these 4 reservoirs to F. And then we get rid of all the clauses in F which contains P. Okay, so in this case, we conjoin this guy with the C1 up to C4. And then we get rid of all the reservoirs and all the clauses that contains P. So this guy is gone. And then this guy will be, I mean, this clause will also disappear. This clause also will disappear. This clause also will disappear. Now, after this step, you can see that P doesn't appear anywhere because, I mean, these 4 are the only things that contains P, and we got rid of all of them. Newly added one, we obtain them by applying the resolution. And then when you apply the resolutions, because P is the one which is canceled, none of CIs will contain P either. Okay? So just to sum up, to say the third step again, the third step is, if P appears positively and negatively, we group all the clauses we group clauses in F into 3 groups, those containing P, those containing negation P, those containing neither P or it's not P. So then for every clauses, all the pairs of clauses containing P and not P, we apply the resolutions, and then we add all the result of the reservoirs from the application of the resolution, and get rid of all the clauses that contains P. Okay, so that's what the step 3 is doing. So it's a bit like doing some kind of cross products. We kind of consider all the possible combination in the third step. And you can kind of see that where the computational complexity goes up. Step 1 and step 2, the number of clauses in the formula that we started with will be just reduced when you produce a new formula. But in the step 3, the number of clauses in the resulting formula might get might get increased quadratically, because we are thinking about the kind of several combinations of 2 clauses inside of the given formula F. Okay, so let's clear drawings. So I will show you some examples here. So if I eliminate P in this, suppose this what you see in this line is the formula that we are given, represented as a set. If we eliminate P, then this falls into the third case. Okay. It falls into the third case because P appears positively as well as negatively. And it happens that in this case, just P, the clause that contains the positive occurrence of P, there's only one. Clause that contains negative occurrence P, there's only also one clause. So we just apply the resolution between these two. If we apply the resolutions, then resolution essentially cancel this positive occurrence and negative occurrence, and we produce Q. Okay, so we will conjoin this entire formula with Q, And we will get rid of, that's the first step. The next step is we get rid of all the clauses that contains in P. So this one is gone. This one is also gone. So then the remaining one is Q and the rest of this. Okay, that's what you get see in the next line. Okay, so here's some exercise I want you to do. So for this next formula, which is represented as a set, I mean, we're having some set representation. Remove R from this formula. Okay, I will give you 2 minutes to do this. Maybe 1 minute to do this. Okay, so let me show you how to do this. So we want to get rid of R, and R in this case appears, I mean, here's a positive occurrence of R, and also here's a negative occurrence of R. So we have to apply resolution for all the possible combinations. So we have to apply resolution proof to this guy, and also to these guys, and these two, and these two. So we have to apply resolution 4 times. If we apply the resolution 4 times, here's what we get. So by applying resolution to these two, R gets canceled, and we obtain not Q and ST. Apply resolution to proof of the resolution to this one, and yeah, to this one and this. Then this R and negation of R get canceled, and we get not Q and T. Same thing in this case, we have ST. Then the final case, we again have an ST. So, and then if you remove all the things that contains R, the final outcome is going to be Q, ST, and not Q, T, and not Q and ST. So this is the final outcome. So when we apply the resolutions. Now, one thing you can see is in that formula that we obtained, R doesn't appear. So we achieved our goal, which is the variable disappeared here. Okay, but that doesn't really tell me. So the step 1 and step 2 kind of understandable. I mean, it looks like we are not losing anything. So this step 1 and step 2 seems to be a reasonable step. So step 3 seems, I mean, it looks like okay, but it looks a bit mysterious if we sit down and think about it a bit more, because it's whether it really does the right job in the sense of what I described before, EQ satisfiability, and yeah, so in terms of variable elimination, yeah, it does the right job, but EQ satisfiability, it may or may not be do the right thing, and that's what we want to see the next. So here's a result, which is called Elimination Lemma. So what it says is that we have a CNF formula F, that if we remove a variable P in the CNF formula by applying the algorithm that I described in the previous slide, and then we obtain G, then it has two properties. The first property is F and G are equisatisfiable. Their meaning may be different because they're actually different because F may contain P, G may not contain, G should not contain P. So they are talking about different sets of the variables, okay? But in terms of satisfiability, they are the same thing. F is satisfiable if and only if G is satisfiable. And then the second part is that if we are given satisfying assignment A for G, so the A is an assignment for variables in G, which make G true, okay? Because G has G doesn't have propositional variable P, because P is eliminated from, it doesn't really appear in G. But the second theorem said by looking at A and the original formula F, we can find a way to extend A, this satisfying assignment. We can find a way to extend this satisfying assignment with extra binding for P, such that that's gonna satisfy F. Okay, this equisatisfiability is essentially, actually say something like what a bit weaker, but it says something along the lines of this second claim. But the important part of the second claim is it can be determined algorithmically. So there are just some algorithm. So if we have A, which satisfies G, and then there is an algorithm that take A and look at F and figures out how we should set the propositional variable P. How should set the value of propositional variable P. Okay. That's these two statements. The first, equisatisfiability. Second, there's an algorithmic way of extending this satisfying assignment of G to a satisfying assignment of F. Okay, so that's the second statement. Now, I want to, so I know it's not very easy, but I want to try to prove this. I will give you maybe 5 minutes, because I'm gonna show you the proof, but I think the best way to understand the proof is really for you to try. And if it doesn't really work, well, you guys struggle. But then if I explain the key idea behind the proof, you'll have a better understanding what's happening. So I will give you time until maybe for about 5 minutes. So take your time and try to improve this lemma. Okay. So here's a variable elimination. Changon, you're right, but doesn't really matter. Maybe, let me check. So maybe I can mute. Okay. Okay, so let me explain how the proof works. So let's think about the, I mean, we're gonna take care of use this. I'll mainly take care of this case 1 and case 3. Okay. For let's think about case 1. Case 1 said, the first, let's try to prove equisatisfiability. And actually showing equisatisfiability will involve some algorithms that will tell us how we can convert satisfying assignment of G into satisfying assignment for F. That's what's required for this second claim. So if we have a satisfying assignment, so let's think about the first case. Case 1 correspond to Dp occurs only positively in F. Okay, so that's the case. Then we have to show they are equisatisfiable. So the first each case is, let's assume that there is a satisfying assignment A which satisfies F. So suppose this is the case. So then we have to show that that A will also satisfy. We have to construct satisfying assignment for G. In this case, G is obtained by changing all the occurrences of a P by true. But one thing we do know here is that since P occurs only positively in F, which means that inside F, if you look at this, P only appears in a positive form. So one thing we can claim is if we replace from the assignment A, if we replace its binding for P to possibly false to true, if it's true, it's just leave it there. That will also satisfy this formula F, okay? Because P appears positively. If originally A set P to false, setting P to true, that will also, more likely to satisfy F because, once you do it, you don't really need to worry about these two cases anymore, okay? So this is the case. But if this is the case, So then that means A, I mean, P is true. That's also going to satisfy G. I mean, because G is nothing but F where we replaced P by true. Okay. So since we, I mean, this we just obtained G where by replacing P by true in F, I mean, that this A will continue to satisfy G. I mean, okay, so that's how you can show if we have a satisfying assignment of F, we can create a satisfying assignment for G. When you can view it this way, or if you prefer, because P doesn't appear in F, we don't, I want my satisfying assignment doesn't have a binding for P, then another thing you can do is from A, you get rid of binding for P. You just remove the binding for P. That will still satisfy G. It's because in this G is obtained by replacing P by true. So essentially, it means checking whether this guy satisfies G or not. It's the same thing as checking this guy satisfies F. Okay, so that's how you can prove one side, and then another side is that now suppose we have G. No, so we have satisfying assignment A, which satisfies G. Okay. So in this case, let's assume that A, well, it doesn't really matter. So then now, if we extend A, where P now bind true, that will continue to satisfy G because, I mean, P doesn't appear in G. Furthermore, it will now going to satisfy F. The reason is if you compare the G and F, G is obtained from F by removing all the clauses that contains P as a positive occurrence, okay? But now P is bound to true, so all these missing clauses from F, when we get G, they will be satisfied. So this property is going to be true. And so just to sum up, from A to A satisfy F, we use this positive occurrence property and said F is still true under A with P is bound to true. And then that implies that if you get rid of P from A, that will satisfy G. Because of it, that's essentially say the same thing. For the other direction, if we have a satisfying assignment for G, then because G doesn't contain propositional variable P, we can bind P to true. That will still satisfy all the clauses appearing in G. And now we still have to satisfy some clauses deleted when we go from F to G, but setting P to true will make those things true. Okay, so that's how you can go for this. I said something very complicated, but the reasoning is actually pretty simple in this case. The more difficult case is step 3. For step 3, going from, so say F satisfiable to G satisfiable follows from by resolution lemma. So in the resolution lemma, we said if we obtain some clause resolvent R from C1 and C2, and C1 and C2 are in F, there are clauses in F. If that's the case, F is logically equivalent with F together with R. So that's what resolution lemma said. And then if you look at the step 3, all the new clauses we added are by applying this resolution. Exactly, I mean, this step. So everything which is added will not really change the meaning. I mean, it will preserve the semantics or meaning of the original propositional formula. So everything added in this step, so all the reservant that's added in this step, that will not make f any change, introduce any change in the meaning of f. So the f will be in the same thing as f together with some newly added clauses C1 up to CK. Okay, so if f is satisfiable, exactly the assignment is going to satisfy it on the right-hand side. And then if you get rid of some of the clauses by deleting this step, the satisfying assignment will still satisfy this. So we get a satisfying assignment. Okay, so that argument shows if f is satisfiable. So that's the argument that we shows this direction. If f is satisfiable and g is satisfiable, say again by resolution lemma, all the extra things that we add by applying the resolution preserve the meaning. It just induced the equivalent formula. So satisfying assignment of f will become satisfying assignment of g. So that's what's happening in step 3. Now the going opposite direction is the part which actually is the key part of this proof. Okay, so then the question becomes, so this is the remaining question, and this requires a bit of thinking. Okay, now, so to prove this, let's suppose we have satisfying assignments A for G. So suppose this is true, and then for G, let's think about how some process that we applied to obtain G from F, which means that inside F there were clauses, means say C1, C2. I use C here. That's not very good, but so there are M clauses, D1, D2, Dn clauses, Dn clause, and I'll just use P. Okay, we have CDE. So there are remaining clause E1 up to EK, where these are the guys which contains P. These are the guys which contains not P. This one doesn't contain P, or doesn't contain not P. Okay, so in such a case, we apply the resolutions to all of these combinations, like C1, C2, and so on, and we obtain the reservants. So the G is obtained by essentially removing every C, removing every D, but then kind of adding all the reservant. So we add the reservant, say IJ, which is obtained from CI and CDJ, and by removing P, so Rij is really Ci minus P union DJ minus negation P. So that's all the reservants, and then G becomes messier. So then G has this form, which is R11 up to Rm because of the older combination, and then it also have E1 up to Ek. And now we have a satisfying assignment A. So we have a satisfying assignment A for G. And one important property that's maybe some space. So let's get rid of these guys. Okay. So we are in this form. Now A satisfies G. Okay. So then here's some property I want to show. If that's the case, so A satisfies G, that implies then we have either A satisfies every CI. Okay, let me measure. That's for C1 minus P. Cn minus P. Or A satisfies D1 minus negation P and Dm minus negation P. So okay, so that's the so afterwards have this form. We by applying the resolution, we obtained G here, and then A satisfies G. Then because A satisfies G, it happens that it has a very special property, which is A satisfies all of CI's without P, or A satisfies all of DI without negation of P. Okay, this is not entirely obvious. Okay, I mean, we just know that A satisfies G, which have this form, and then we also know our I's are constructed in this way. Okay, from there it follows the A satisfies all the C's without P, or A satisfies all the D's without negation of P. Okay. Why that's the case? And that's, I mean, we can check this by contradictions. I can say it's why. So if that's not the case, that means there exists. So if it's not, then there exists a CJ, which is not true, doesn't hold under A, and also there exists, maybe using I is better. And then there's also DJ, which doesn't really hold under A for some IJ. Okay, so there exists some CI without P, which doesn't hold under A, and also DJ without negation of P, which doesn't hold under, under A. Okay, I mean that's just negation of the either all of this true or this true. Okay, and actually this is not either. It means so. Oh, that mean if you take a if this is not this what I underlined with the red line is false. So then this is the consequence. But then if this is the case, like if A doesn't satisfy Ci minus P, and then also A doesn't satisfy Dj minus negation of P, that means A doesn't really satisfy Ci minus P union. So these are disjunctions of litters. Okay, so union means disjunction of litters. I mean, we are just taking the disjunction. So let's just use a disjunction that makes things a bit clear. Because A doesn't satisfy this guy, Ci minus P, A doesn't satisfy Dj minus negation P. If we take a disjunction of, Ci minus P and Dj minus negation P, that's not going to be true under A either, okay? Okay, so that's just the meaning of disjunction. So, but what you see here is exactly Rij, which is a result of the resolution. And then this Rij appears as one of the conjuncts in one of the clauses in G. And then A should satisfy all the clauses in G. So there's a contradiction. Okay, so that's why in this property is true. And now so because of this property, because A satisfy all the C's or all the, A satisfy all the C's without P, or A satisfy all the D's without negation P. We do case split based on whether the first case is true and second case is true. If the first case is true, then we set the value of, okay, if the first case is true, so then what we do is we say we extend A by binding P to false. Okay. So now then what happens? What happens is if we do so, then this extended A with P is bound to 0. It's going to satisfy every Ci because A already satisfy Ci minus P. So all of this will be true. So if we go back to the original F, that will take care of, okay, maybe this extended A will all satisfy all of these guys. That's because, we are talking about this case. And also because we set P to 0, it will also satisfy all of the i's. They contain negation of P. And if P is 0, then this will become 1. So all of the i's will be true. And then EI's, they don't contain P or negation of P. So that's gonna be true because the formula A, the assignment A that we started with is already satisfies G. Okay. So then the other remaining cases, there's opposite case, and if we use this, there's opposite case which talk about A satisfies this Ti minus negation of P. In that case, we can extend A by setting P to 1. Then exactly the complementary situation happens. Under this extended assignment, these Di's will be true because A already satisfies each of Di's even when we get rid of this negation P. And then because P is set to 1, all the Ci's will be true. And then EI's will remain to be true because A already satisfies G. Okay? So it's a bit complicated reasoning, but the reasoning is starting from F, we see how G is obtained. And then if we have a satisfying assignment A for G, then actually the satisfying assignment have a very special property, which is it either satisfies all the C's without P, or it satisfies all the D's without negation of P. And then we do the case analysis based on this. Okay? So this A that's claimed in the theorem is the way we can obtain this A is by doing this case analysis here. Okay. Look at the case analysis. If A satisfies the above case, then we set A to 0. If A satisfies the below case, we set A to 1. Okay. So that's how you can construct this A. And that's actually a part of the algorithm. The algorithm is when the David Putnam's the variable elimination algorithm is run recursively on G. If it returns a satisfying assignment, it does this checking. We check whether A satisfied this case 1 is true or case 2 is true. Case 1 is true. It extends satisfying assignment by setting P to 0. Otherwise, it extends satisfying assignment by set P to 1. Okay. So that's it for. And now here the algorithm is exactly what I told you before. So David Putnam algorithm take conjunctive numeral form formula F, and then it keep removing one variable. But it does some simple optimization. So it remove all the valid clauses from P. By valid clause, I mean the clauses like if I have a clause which contains P and negation P and something, this will become same as true. So you get rid of all the clauses of this kind. And then now for the remaining clause, if it's just containing this box, singleton set with a box, it will return unset. Otherwise, it said it's a satisfiable. And then what we return is an empty assignment. We return essentially empty map, which doesn't do anything for the propositional variables. Okay, so otherwise, so these are the two base cases. Otherwise, F contains some propositional variable, and we pick one of the propositional variable from F, and we get rid of it by the variable elimination step that I told you. And we make a recursive call on this formula G, which have a one fewer propositional variable. If that returns unset, we just return unset because variable elimination preserve the satisfiability. It's F and G are equally satisfiable. So that's the one consequence, property we are using here. For the second case, if G is satisfiable, so then we extend this satisfying assignment A with this extra binding for the eliminated variable P. And this extra binding happens by the case analysis that I showed you in the previous slide, which is we just look at all the clauses that we used when we, especially the third case, we look at all the cases where we apply the resolutions, and we divide them, group them into the clauses containing positive occurrence of P, clauses containing negative occurrence of P, and see which one A satisfies all, and then based on this we make a decision. Okay. So let me just apply the algorithm to show you concrete examples of the run of this algorithm. Maybe it's better. Okay, so here the algorithm works. So we suppose we are given the original formula. The original formula is of this form. Then the first, suppose that the David Putnam algorithm pick variable P. So then P appears positively as well as negatively, so it get rid of it. So we apply the resolutions. Then that resolution will produce, resolvent, which is what I mean. There's this negation of P, and then it get rid of all the clauses that containing P1 negation P. So these two guys will be removed. In the second step, so it try to remove, apply the resolutions, remove the variable Q. So now we have Q negation of Q here and Q here. So we apply the resolutions that will remove these two variables and then produce a resolvent, which is the singleton set R. And just like before, we remove all the clauses that contains the Q or negation of Q. And the same process applies. So that same process get rid of, produce the resolvents. This guy, when we apply the resolutions on these two clauses with respect to the variable R, and then the two original clauses containing R and negation R will disappear. But at this point, it's one of the base cases because S now appears only positively. So we set S to true and simplify. And if you simplify, this entire thing disappears. It's a clause containing, it's a disjunction of S or negation T. And if you set S to be true, then the entire clause will be true, so it will disappear. So we reach one of the base case. The base case is say we have a satisfying assignment. So then the entire result will be set. It's just the original formula is satisfiable. Now we have to construct the satisfying assignment by going backward. So when you go backward from here to here, so for T, it doesn't appear anywhere. So any value you can set for T is okay. So in this case, we set T to 0. For S, we replace S by true. So S will be set to 1 here. So that's what these two things is what we get when you go in this step. Now for the next one, okay, this is a set assignments, satisfying assignment A. We use this satisfying assignment A and see that whether it satisfied all, so this is a step that we are in, whether it satisfies all the clauses containing P or all the clauses containing negation of P. And I mean, in fact, in this case, the 0 and the 1, that satisfied all the clauses containing negation of P. So maybe using different color is better. So in this case, it satisfies, this guy, that's because S is equal to 1, and this clause is true. So S is equal to 1 and negation T is also true. So this is satisfied this case. So we set R so that the remaining case to be true. So R is going to be set to 1. And we do the same thing. Now this becomes a new A. So it's a, say, A1. Let's call it A prime. It's only A prime. And under A prime, we say that which clauses will be true. And then under A prime, this clause, it doesn't contain any Q, but for clauses containing Q or negation of Q, it satisfies all the clauses that contains Q, okay, because R is 1, so this is true. So then we say now negation of Q should be equal to 1, which means Q now should be set to 0. So that's why we get this next case. And then the A double prime becomes the satisfying assignment of this form. And for this satisfying assignment, we do the same thing. We look at the clauses containing the negation of Q or Q. So these are the two clauses here. And we see which one, so whether it satisfies all the clauses containing all the clauses containing negation of Q or all the clauses containing just P. No, negation of P or just clauses containing P. In this case, all the clauses containing negation of P will be true under A double prime. So P is going to be set to 1. Okay? So that's the final outcome that we can construct from here. So it's the run of this algorithm. So then the time complexity of this algorithm can be, in the worst case, it can be exponential. That's because whenever we eliminate one variable, if we hit the third step, so this is third step, then potentially we have a quadratic blow up. So if we have n variables, then the size can grow exponentially. So the size of the formula can grow exponentially. So that's why, in the worst case, it takes exponential complexity. But then we can ask various questions like, and also the performance of this algorithm depending on which variable eliminate first. Okay. Right. And then so we can ask various questions like the one that I showed you on the slides. And having a good answers for these questions is actually a research problem. So I myself don't really know the answers for which variable to eliminate for first, or maybe what are the impacts of eliminating one variable right now. But I think maybe some of you don't really care about what's really going on, but some of you who care about it, I encourage you to think about these type of questions in your spare time. Okay, so just to sum up for this part, we covered the resolution. I mean, I explained the resolution as a proof calculus and showed that it's a sound and complete. And then I showed you how we can use resolutions, so-called David-Putnam variable elimination, which is based on resolution, which tells us how we can use resolution calculus to have a decision procedure, or have an algorithm for checking satisfiability for propositional logic formula. And although I didn't show you, it's this David-Putnam algorithm for nice formulas, like I don't remember exactly what they are, but for some nice class of formulas with certain restrictions, this algorithm, we can show that it runs in polynomial time, but although it has a worst case exponential time. Okay, so that's it for the resolutions and David-Putnam algorithm. And maybe I have about 8 minutes. I can rush, or maybe I will give you some general overview of the next topic and then maybe finish a bit early today and get questions from you if you have any. So the next topic, which I'm going to talk about on next Wednesday, is a Dpl algorithm. Likely, Juyeon, I think your guess is right. It's likely the Horn formula and tool set, but I can't say for sure because I forgot what nice formulas actually means. So it's what my colleagues wrote. At some point, I understood what they meant. My guess is exactly your guess is right, but I can't tell you for sure. Okay, but very likely Horn formula and so on. Okay, so the next topic is a Dpl algorithms, and I want to just give you some overview about this idea behind the Dpl algorithm. So, this Dpl algorithm is combining search, and so interesting bit about Dpl algorithm is it's combining the idea of search and deduction. Okay, so and then it's especially if it combined with the closed learning, it contains the idea of learning, but not in the sense of what you see from the statistical learning or machine learning, but more in the sense of if you say I failed something, I got a very bad marks in the exams, so then I take a step back and think about what I did wrong, and that may give us some idea about how should I improve next. Okay, so it's like think about failure. That thinking about the failure may help you identify the core reason of the failure, and that may help you to do much better in the next time. But that's the kind of thing that's happening in this Dpl algorithm. It does learning, but the learning is based on deduction and thinking. And other interesting bit about this algorithm is it combines the idea of deductions, which is like doing some form of logical deduction, and also another aspect which is called search, which is really a bit like doing case enumeration. So here's some quick overview about this algorithm, then I will finish. So if you think about search, the search, you kind of imagine the search tree, okay? So we start with some, we start with some choice, and then there are multiple possibilities for the next one. If it's a plain Paduk or maybe some other search problem, there are multiple possibilities. We pick one of them, and then we explore other possibility and so on. We keep going. So it's a depth first search, start, continue. And then finally we reach the end. If this is good, then we are done. But if this is bad, we backtrack. So depth first search, base idea of depth first search is like this. You just make some decision and make bunch of series of decisions among the possibility. If you happen to hit a good case, you're done. Otherwise, you backtrack up to some point. And then, so next time you try something different, okay? So backtrack up to maybe here, and you try something different. So that's a typical way of doing search. But now to improve the performance of search, here is something that you have to do. The one thing you have to do is that whenever you need to, there are multiple possibilities. If there are multiple possibilities like this, I mean, instead of exploring all these possibilities, you based on some idea, you do pruning. Okay, you say, oh yeah, if I look at, I mean, this subtree, they are useless because they, although I didn't really go all the way until the end, I know that they are either leads to suboptimal answer or maybe they don't give me an answer at all. So you do the pruning, you prune the possibility of search, and then you just explore the remaining one. Okay, so that's a kind of idea of the search. DPLL in a sense follows the same kind of idea, and this pruning step is done by deductions. And then next time we're going to talk about it is called unipropagation. And then the idea of learning is that now suppose I follow this path, but I failed again, so I ended up with a bad case. And then the algorithm actually analyzed these failed choices. So failed, I mean, this path is a failure path. It analyzes this path, and then it gathers some knowledge. Okay, you say, okay, what's the main reason I failed here? And that knowledge will help you to do the pruning next time much, much better. So that's how this algorithm is working. And then to identify the core reason of this failure, it uses resolution. I mean, the one way to do this is using resolution. So this closed learning will correspond to this step. Okay, so that's an overview, and that's it for today. And I will tell you more about this Dpl algorithm on Wednesday. Okay, so I'll stay here about 5 more minutes. So if you have any questions, ask me. And you can go home, I mean, if you don't have any questions.